with vectors, we've talked about two vector operations so far. Vector addition and scalar multiplication. When we add two vectors together, we always get a vector. If we multiply a vector times a scalar, which is just a real number, you still get a vector. Today we're going to talk about this third type of vector operation, and that is the dot product. It's not really multiplying the vectors together, it is a dot product. And when we take the dot product of two vectors, we get a number, a scalar, not a vector. So, example, if vector u is, we'll call that u1, u2 in component form. Those are the components of vector u. And we have vector v, and I'm going to say that that is v1, v2. The dot product of u and v we find by multiplying together u1 times v1 and adding that to u2 times v2. So when we do that, we'll always get a scalar. Instance, if we have the vectors component form 3, 4, and I want to take the dot product with the vector in component form 2, negative 3.
Why is it called dot product?
I don't know. Somebody made that determination because it's a dot. And we can get, here we'll have 3 times 2.
So, like, if you make up something in math, can you call it whatever you want? Is it like science that way? Like if you discover
If you
some
discover it, I guess so.
operation, so like if you discovered an operation, you can call it the Colville. Like, we're gonna take this and we'll Colville it with this.
I guess if I had discovered an operation, but somehow I don't see that
That'd be
happening.
awesome.
So this is equal to negative 6.
Just Colville the 6 by 2.
All right, let's take this dot product.
Newton is called Newton because of the voice.
What do we get here?
0.
0, because 2 times 1 plus 2 times negative 1, so here the dot product is 0. So it's easy to find a dot product. The dot products have some properties. Get some properties of the dot product.
Those letters, 3 and 2 and 4 and 3, where are they? Like they are in them from, we have to drop them inside, no?
What?
Like
Properties of the dot product. If u, v, and w are vectors. Nicholas.
I was explaining something to a student.
And k is a scalar.
Was it a math coincidence?
Then these are some of the properties of dot product. The dot product of u with v can be rewritten as the dot product of v and u. Commutative property. If we take the dot product of a vector with 0, we get 0.
So these are just regular lines.
If we take the dot product of u with v plus w,
UV plus U.
that's the same as the dot product of u and v plus the dot product of u and w. These look like some of the same properties that have always, we've worked with for years and years and years.
So why-
Looks
why
like the
do we do that?
distributive
Why do
property.
they have to say the properties again?
So
if
you
it's the
know
same
that they work
properties?
with the dot product.
It's
I can't move that one.
We used to just live with this multiplication, it has the same.
It's not multiplication, it's a dot product. The dot product of a vector with itself
Isn't product multiplication?
is equal to the magnitude squared. That's new.
This is where you lose us.
Wait.
The dot product of a vector with itself equals its magnitude squared.
So would that mean that dot product equals magnitude?
Squared.
Yes, but if dot product times dot product equals magnitude squared, wouldn't that mean that dot product?
The dot product of something in itself.
Ah,
Dot product is
You're
a
overthinking
variable.
this.
I stopped caring.
Dot product is a
I
process.
stopped caring, you can stop now.
All right, if we take a scalar times a dot product, we could, it's a dot product. We could do KU with the dot product of V, or U dot product of KV. So we're going to look at some different examples of that in just a second. All right, if U is 3, 4, vector V is -2, 6, and vector W is 1, -1. First, I want to take the dot product of U with V and multiply that by vector W. All right, so the dot product of U with V is going to be 3 times -2 plus 4 times 6. And I'll multiply that by vector W. So we have 18 times vector W. And vector W is 1, -1, so my final answer is 18, -18. Here we get a vector.
So
When you multiply a vector times a dot product, you get a vector.
when you multiply 18 by W, but it's just 18 times 1, 18 times.
Yes, yes. Andrew?
Didn't you say that when you do a dot product, it becomes a scalar?
Yes.
And K is a scalar.
No, the dot product.
No,
is
W
equal to
is this
V.
vector.
Andrew, the dot.
Oh,
product-
and K in the
And K,
properties is a
yeah.
scalar.
Okay.
Yes, yes.
So it turns into a scalar and then it's just basically putting it into the,
We're multiplying it by the vector.
okay.
A scalar vector.
Miss,
A scalar is just a real number.
-3 and plus 24. You did a part plus 6 and plus 24.
That's 18.
Okay, yes, but that's the dot product of U and V, no?
Yes.
Okay.
All right, let's look at another one. If I take U, the dot product of U and 2W, well, what is 2W?
2W is going to be
2, -2. So if we take the dot product of U and 2W, we get 3 times 2 plus 4 times -2. So that dot product equals -2. And that is a scalar. Dot product results in a scalar. The previous problem, we multiplied a dot product times a vector, which gave us a vector.
That's not a property, no? Or yes?
Well, it's really scalar multiplication on this one. That becomes scalar multiplication. We multiply a scalar times a vector.
Okay.
All right, remember the dot product of a number with itself, or a vector with itself is equal to the magnitude of the vector squared. So if I said that the dot product of u with itself is equal to 7, what is the magnitude of u?
Square root.
The square root of 7. Because the dot product is the magnitude squared. The dot product is the magnitude squared. So if I tell you that the dot product is 21 of a vector with itself, what's the magnitude of the vector? Square root of 21. All right. Another important use of the dot product is to help us find the angle between two vectors. And that's what we're going to be looking at for the rest of the time today. If we have vector u and vector v, those angles, or those vectors, have an angle between them. And the formula to find the angle between those two vectors is the cosine of theta equals the dot product of u and v over the magnitude of u times the magnitude of v. The cosine of theta is the dot product of u and v over the magnitude of u times the magnitude of v. That gives us the angle between the two vectors. You'll have to use the arc cosine to get that angle to find theta. But this is the formula that we plug into. So if we have vector u, which is 4, 3, and vector v, which is 3, 5, I want to find the angle between those two vectors. So first of all, I need to know what is the magnitude of vector u.
Is times magnitude of u times magnitude
Yes. What's the magnitude of vector u? 5. That's those numbers that all come up a lot. But we're going to have to work out v.
It's this
Square root of 16 plus 9.
4. Square root of 34.
All right, so the magnitude of v is the square root of 34. So to find the angle between the two vectors, we take the dot product, which is 4 times 3, 12, plus 15, over 5 times the square root of 34. Now you'll have to use on your calculator the arc cosine.
27.
Thank you. So theta is did you use arc cosine?
You're at 22.
22.2 degrees.
22.2.
All right, let's use vector u is 3, 0, and vector v is 1, 6. Find the angle between those two vectors. All right, the cosine of theta, what's the dot product?
3.
What's the magnitude of u?
3.
What's the magnitude of v?
Square root of 37.
Be sure that you put this in parentheses. So theta equals 80.54 degrees. Vector U is negative 1230. And vector V is 5/4,
Theta.
1/2. Find the dot product here. Find the angle between those two vectors.
Okay, calculator's going to be.
Is that the angle between them? What'd you get for the dot product?
0.
You got 0. The cosine of theta equals 0 over something, which is 0, right? The cosine of theta equals 0 over some number. I don't remember what the magnitudes are, but you do have some number down here. What angle has a cosine of 0? 90. These vectors are perpendicular. Another word for perpendicular is orthogonal.
What?
Orthogonal. That means that if lines are orthogonal, they are perpendicular to each other. And if two vectors are orthogonal, the dot product is 0. So you can easily check to see if two vectors are perpendicular by checking their dot product. If they are perpendicular, their dot product is going to be equal to 0. All right? So that's a quick little check to see if you've got two vectors that are perpendicular. Now we said that the formula to find the angle between two vectors is the dot product over the magnitude of each vector. An alternative form of the dot product is if I multiplied both sides by the magnitude. Cosine of theta times the magnitude of u times the magnitude of v. This is an alternate form, and it's also the formula for work. It's a physics. Work, yes, work equals, in other words, we could think about this, work is equal to the cosine of theta times the force required to do something, or move something, or lift something, times the distance. Okay, this is another physics application, so don't ask me why. I'm not a physics person, but work is defined as the cosine of theta times the force required to do something, if you're moving something or lifting something, times the distance. So
that's not a dot product of force and distance.
pardon?
You use this.
No, it's multiplication.
Wait, so that is a new formula? U times V equals...
It is just an alternate formula for this. I just multiplied both.
Symbol for dot product and multiplication.
I don't know. Because we don't really multiply vectors together. All right, so let's look at this. We have a force of 50 pounds. That is needed to close a barn door. At a constant angle of 60 degrees.
tilted 60 degrees.
We want to find the work required to move it 12 feet.
Yes,
Oh,
but
the angle of the door is open from the wall of the barn is 60 degrees.
We want to find the work required to move 12 feet. So work equals the cosine of 60 times 50, that's the force, and the distance is 12. So that's just a plug in your calculator answer. We know that the cosine of 60 though is 1/2. So we would have 1/2 of 50 times 12. 6 times 50 is 300, and we call this foot-pounds. Again, that's a physics term. I'm not sure why somebody came up with that, or why they decided to measure it that way, but it's in foot-pounds.
They're a genius.
To slide an object across the floor. Shh. A person pulls a rope with a constant force of 25 pounds. At a constant angle of 30 degrees above the horizontal. Find the work if we drag it 40 feet. All right, so again, work equals the cosine of 30 degrees. The force is 25 pounds. And we're going 40 feet. So the square root of 3 over 2 times 25 times 40. And that is
866.03.
about 866 foot-pounds. If you lift something vertically, then you don't need an angle.
Is there like a practical use for foot-pounds in some industry somewhere?
bow draws making foot-pounds.
If you lift something, if you just lift something up from the floor this way, there's not going to be an angle.
Foot-pounds of force control.
90.
No, it's just pounds.
But you don't have to work, we won't use an angle associated with that if there's a vertical lift. All right. After lunch, you have a quiz.
Yay!
And your assignment is 8 to 36.
Yay!
Every fourth.
That's a lot.
Every fourth, that's not a lot. 50 to 58 even.
Oh my gosh.
And what's that, 78 to 82 even?
Yes.
Is it 78 or 76?
It's 78 to 82.
The force doesn't come from your arm, it comes from your back.
In the world, you can't go back.